Hello everyone, welcome to today's live broadcast entitled HPLC Troubleshooting, Conquering Common Challenges. I'm Jerry Workman, the Senior Technical Editor of LCGC, and I'll be your moderator for today's event. We are pleased to bring you this webcast presented by LCGC and sponsored by PerkinElmer. PerkinElmer enables scientists, researchers, and clinicians to address their most critical challenges across science and healthcare. With a mission focused on innovating for a healthier world, we deliver unique solutions to serve the diagnostics, life sciences, food, and applied markets. We strategically partner with customers to enable earlier and more accurate insights, supported by deep market knowledge and technical expertise. We have a few important announcements before we begin. This webcast is designed to be interactive, and we encourage you to ask questions during the event. You can submit questions by typing them in the Q&A box, which can be found on the right-hand side of your screen. You can enlarge the slide window by clicking on the small square icon in the upper right-hand corner of the slide window, or by hovering your mouse over the lower right-hand corner and dragging the window to the desired size. The slides will advance automatically during the event. If you have any technical problems viewing or hearing this presentation, please click on the question mark help widget in the dock at the bottom of your presentation window. I would now like to introduce today's speakers. We are pleased to be joined today by Matthew Prispichel and Catherine Lawson-Wood. Matthew Prispichel earned his PhD in analytical chemistry from the University of South Carolina. The focus of his research was development of new stationary phases for capillary gas chromatography. Upon graduation from the University of South Carolina, he accepted a position at the Rohm and Haas Company. During his time at Rohm and Haas, he developed GC-based continuous air monitoring systems for the ultra-low level detection of hazardous airborne chemicals. In the late 1990s, ES Industries focused its efforts exclusively on chromatography column products for HPLC and SFC. Matt has become Vice President and Technical Director for Chromatography Products at ES Industries. He has successfully developed and commercialized a number of chromatographic stationary phases and columns for high-performance chromatographic separations for HPLC and SFC. Recently, ES Industries has become part of PerkinElmer Health Services, and Matthew is now in product development at PerkinElmer. He has published articles on the development and application of new stationary phases for GC, HPLC, and SFC. Catherine Lawson-Wood is a commercially focused product leader with the consumables business unit at PerkinElmer and rejoined the organization in July 2017. Prior to this, Catherine studied for a Bachelor of Science with honors in chemistry at the University of Surrey in the UK, with an industrial placement year at PerkinElmer. Her role as an application scientist involved the research, design, and execution of application notes to demonstrate solutions for emerging food and environmental issues. Primary focus was on food packaging analysis, water analysis, and food authenticity testing, using various techniques including molecular spectroscopy and chromatography. Since rejoining PerkinElmer, Catherine has focused on providing product and application support for PerkinElmer's consumables business unit as a consumables product specialist. During her time in this role, she developed application notes and technical data to support new product introductions, as well as evaluating alternative products. In addition, Catherine frequently liaised with global product specialist teams to understand key market trends and provide pre- and post-sales technical support. In her current role as a consumables product leader, Catherine is involved in activities including development of strategic collateral for new product introductions, product training, and driving sales enablement by liaising with regional commercial sales and service support teams. Thank you both for joining us today. Catherine, please get us started.
Thank you, Jerry. Welcome to our HPLC troubleshooting webinar. Today, we will discuss how to identify, isolate, and correct the most common HPLC problems in order for you to improve your lab productivity and yield the most success in your future analyses. We will cover the following topics, including common peak shape issues, retention time repeatability, baseline effects, and column deterioration. So just to provide a quick overview, you'll all know that an LC system consists of a pump, an injector or auto-sampler, column which can include a column oven, a detector, and then also the data system or integrator. As an example, to the left of the slide shows the new PerkinElmer LC300 HPLC system with a UV detector, auto-sampler with an integrated oven compartment, a pump with an integrated degasser, and a power and waste module. Now, all components in any LC system can lead to problems in chromatography. So if performance is not what you expect it to be, you should firstly verify that a problem exists. You should check your system with a known sample on a known column and then compare your results with documented reference points. If there is a problem, then do the obvious or easy things first. This could include inspecting the system for leaks, trying to swap out modules if possible, and using the instrument's built-in diagnostics. It's vital that you only change one thing at a time during troubleshooting to ensure you know which variables influence the problem and which do not. Often it's tempting to change several things together just to solve the problem, but in the long run, this does not help you identify the real issue to avoid or minimize future issues. You may also consult manuals, troubleshooting sections, and also experts. Finally, consider when your last maintenance was and whether you have preventative maintenance scheduled for your instrument. Generally, LC instruments should have a PM every 6 months to 1 year, depending on use. So firstly, I'd like to go over common issues with peaks in terms of peak shape. Generally, there are 4 common issues with peak shape, which include tailing peaks, fronting peaks, split peaks, and broad peaks. Symptoms do not necessarily affect all peaks in the chromatogram, and each issue may have multiple causes, so it can be difficult to get to the root cause. In terms of peak shape, tailing factor is a measure of peak tailing and is calculated at 5% peak height. The tailing factor of 1 indicates a perfectly symmetrical peak, and this is the ideal scenario as it makes peak integration a lot easier and improves resolution between peaks. Peak tailing occurs when the tailing factor is greater than 1, and peak fronting occurs when the tailing factor is less than 1. And you can see a couple of examples on the top right which show both of these scenarios. Generally, a tailing factor between 0.9 and 1.2 is considered acceptable for a new column, and practically a value below 1.5 is usually okay to work with, and a value of up to 2 may be acceptable depending on the separation and resolution of the peak. If the tailing factor is above 2, then it can indicate an issue. One thing to note if you observe peak tailing or fronting is it a problem with all peaks or just a select few? So if only some of the peaks tail, then it's highly likely that there are some unwanted secondary interactions between the analyte and the stationary phase, such as residual silanol interactions, which I'll go over on the next slide. It could also be that the mobile phase pH is too close to the sample pKa. Alternatively, the apparent tailing may just be a small peak eluting on the tail of a larger peak, giving the appearance of peak tailing. So to counteract the effect of secondary interactions, you can use a highly deactivated column, for example, one that has very low metal ion content and is processed in such a way that the surface is much less acidic. You could also operate at a lower pH to minimize secondary interactions. Additionally, if the sample is easily ionized and the difference between the pKa of the sample and the mobile phase pH is less than 2 pH units, then tailing can result. You should ensure that you increase or decrease the mobile phase pH to be at least 2 pH units away from the sample's pKa to reduce tailing. Another option is to use a buffered mobile phase or increase the concentration of the buffer if used already. Finally, if the tailing is a result of a co-eluting peak, you can adjust the method to prevent this. So what is silanol activity? Basic compounds will frequently interact with unreacted silanols on the silica particles, and these are just hydroxyl groups on the silica surface. This is an unwanted secondary retention which causes analyte to be retained longer than the bulk of the analyte molecules, which results in peak tailing and impacts on the separation efficiency of the column. A greater number of residual silanols will result in greater peak tailing. Hydrogen bonding and ion exchange are thought to govern the interaction process depending on the pH, and the interaction is most problematic when the packing is used around pH 4 to 8, where silanols and many basic compounds are partially ionized, and ion exchange governs the interaction process. Silica purity is also an important factor, as surface metals can activate a silanol to make it very acidic, which then becomes even more likely to interact with basic analytes and therefore lead to peak tailing. Traditional type A silicas have much higher metal ion content than more modern type B phases, so you get much higher peak tailing with the type A phases. So if all peaks tail, then there could be a number of causes. For example, if the peak shape starts to degrade over time, then there could be a column, guard, or frit contamination, or the column might have degraded. Cleaning the column and replacing the guard cartridges can often restore performance. However, if the column has degraded and performance is not restored after cleaning, then column replacement may be required. Additionally, it could be a result of a contaminated mobile phase or poor system maintenance, such as faulty check valves and poor pump seals. You should prepare fresh mobile phases and ensure regular PM visits to ensure the system is in good working condition. If all peaks have always tailed rather than changing over time, it could be due to the data acquisition rate being too low or column overloading caused by excessively large sample volumes injected onto the column. Alternatively, it could be due to extra column effects. So extra column volume is comprised of internal volumes of various system components such as fittings, tubing, autosampler, and detector flow cell. If there is a large extra column dev volume, then this can contribute towards tailing, so optimization to minimize these volumes is advised. Peak fronting is more rare than peak tailing. You should firstly determine whether, again, is it a problem with all peaks or just a select few. This will also depend on whether the method is gradient or isocratic, as we'll see in the next slide. And it's important to note that if fronting does occur for all peaks, it can be less noticeable for later eluting peaks due to band broadening. So why does it occur? Firstly, it could be due to column overload or specifically sample mass overload, meaning that there is more sample than can effectively partition, which results in some sample preceding the rest of the peak. And this could be resolved by diluting the sample. Secondly, fronting often occurs due to the sample solvent being incompatible with the mobile phase. It's always best to use a sample solvent which is the same composition or weaker than the mobile phase to avoid these effects. Another cause could be due to the column packing or formation of voids and channels in the column. Always check the QC test sheet, as minor fronting could be a characteristic of the column itself. Voids could also form through analysis as well, such as pressure shocks, mobile phase pH being too high, for example, as well. And I'll go into a bit more detail on voids later on when we discuss split peaks. Another consideration is that the apparent fronting may not be a true fronting peak. It could be another sample component co-eluting. So an example of a sample solvent incompatible with the mobile phase or strong solvent effect is shown on this slide. In this case, this is a gradient analysis where the sample diluent is much stronger than the starting composition of the eluent. At the start, the peaks show a lot of fronting, which eventually is resolved as the eluent strength is increased throughout the gradient run. So the reason this occurs is that if there's a higher percentage of organic in the sample diluent than the mobile phase, then the analytes behave differently as they enter the column. The figure in the top right demonstrates this effect, where some of the analyte molecules elute through the column much faster than the bulk of the analyte, as the sample diluent is more highly eluting than the eluent or mobile phase. The phenomenon becomes less prominent as the mobile phase organic concentration is increased, to become more similar to that of the sample diluent. Another issue which may be observed is split peaks. So peak splitting is when a Gaussian peak acquires a shoulder or a twin and they have the same base. True peak splitting is not a result of coelution of another peak, which may look as though it is a split peak. Whenever you notice peak splitting in your chromatogram, you should first check if the splitting occurs only in one to two peaks, or if you observe splitting in nearly all of the peaks. If only a single peak is affected, then it's likely to be caused by something related to the separation, for example, a coelution. One way of checking this is to inject a smaller sample volume, and if this results in two distinct peaks, the problem could be coelution, and the method should be revisited to improve the resolution. If most or all of your peaks are affected, however, then it's likely to be a column-related issue, for example, column contamination, voids at the inlet of the column, or blocked frits, which I'll go into a bit more detail in the next couple of slides. It's important to note that peak splitting can also occur due to a poor quality HPLC method, for example, injecting a solvent which is stronger than your mobile phase. So it's generally recommended, again, that the sample diluent is the same or a weaker organic than your mobile phase. When faced with all peak splitting, we must consider a disruptive sample path as one option. So a disrupted sample path can be caused by poor bed integrity, and by this we mean that there may be channeling of the packed bed, for example, a gap between the wall and the packed bed of the column, or a column void at the top of the column, caused by the bed compacting at the top of the column. Channeling allows solvent to bypass the bed, with some going through the packed bed and some going through the channel. So some of the analyte comes out sooner than the rest. Eventually, once the column is channeled, the packing will redistribute with use and form a void at the top of the column. In both cases, voids and channels allow a sample to follow different paths through the column, therefore resulting in peak splitting. And sometimes you can also get severe peak tailing too. Voids at the inlet of the column can be caused by a poorly packed bed, which settles in use, or by pressure spikes, which can disrupt the packed bed and damage the column. Alternatively, erosion of the packed bed, which can be caused by high pH, can also cause channeling, which would lead to a void. It's important to note that partially plugged inlet frits also produce a very similar effect. So how can this be resolved? If the issue is a partially plugged inlet frit, then this can often be cleaned by reversing the column and flushing it without it being connected to the detector. However, if this does not resolve the issue, then there is likely permanent column damage and a new column will be required. Another cause of peak splitting is column contamination, which can be prevented by using guard columns with regular replacement before peak splitting occurs to prevent the build-up of particulates on the column. They should be changed regularly or at the first sign of pressure increase or performance degradation. It can also be prevented by filtering samples and solvents, using inline filters, carrying out SPE sample cleanup, and periodic column washes with higher organic content than your mobile phase. And it's very important to note that if your method is running high aqueous mobile phases, you can run the risk of split peaks. You need to periodically run high organic to remove organic contaminants which build up on the column and need stronger solvents to remove them. So just remember to remove any buffer before switching to a higher organic. If split peaks do occur, first replace the guard cartridges and reverse flush the column. If this does not resolve the issue, then the column should be replaced. Peak broadening and loss of efficiency is another common issue. Firstly, this could be due to column contamination, aging, and maybe even a void at the column inlet. You may find that broadening gets worse over time, and if column flushing does not restore the column, then column replacement may be required. Another reason might be extra column effects, as mentioned before. So if, for example, you change the tubing and it's too long or the ID is too large, then this will contribute to band broadening. Other reasons may be if the mobile phase has changed, for example, the flow rate is not set properly, or the mobile phase composition has changed, that can affect the broadening as well. And this can be resolved by preparing new mobile phases, checking the flow rate, and so on. Additionally, issues with this system could be another reason, such as faulty check valves and pump seals, or even leaks. So now I'll pass over to Matt to discuss other peak issues which can occur.
I'm Matt Priscilla, and I like to discuss other peak issues. One of the situations we have for a peak issue would be no peaks or small peaks. Common causes of that would be detector lamp off. That could be through inattention to the actual detector system or a failure of the lamp itself. So in order to remedy that, we should ensure that the detector lamp is on and functioning properly. Next would be no mobile phase flow. Again, this could be done as a fault of the actual pumping system or a major leak. The key there is to ensure that the pump is on and working. Again, another cause of no peaks or small peaks would be vial position. In other words, a wrong position in an autosampler, an empty vial, a bad sample, or most importantly, a plugged syringe. It is prudent to go through all these parts of the autosampler, especially the syringe. Finally, a major leak would cause no peak or small peaks. So inspect the system, look for leaks, and tighten fittings if a leak is found, and that should resolve the issue. Change in peak height or a decrease in peak height. Causes would be one or more sample components deteriorating or a change in column activity. Another cause would be a leak in the system. Incorrect injection volume, again through a plugged syringe or a faulty autosampler or a low sample in an autosampler vial. Another cause would be detector lamp nearing the end of its life. And finally, worn injector seals or a leaky injector will cause a decrease in peak height. Another area of other peaks would be actual co-eluding peaks, either coming out as appearing to be a single peak or a shouldering peak. Two or more peaks eluding at the same time would be a co-elution. How do you resolve this? We've shown this as two examples in the chromatograms. One would be actually to change the column or change the selectivity of the column. So we could see that in the C18 column in the upper portion, peaks 2 and 3 are co-eluded, and they're co-eluded as a single peak. If we change the column, we're able to resolve or separate peaks 2 and 3. However, if we take the changed column and actually change the mobile phase conditions, we're able to really improve the separation of 2 and 3 to the point where they are baseline resolved. And this is one of the real strengths of the PerkinElmer EPIC column line, is that we not only provide C18 columns, but we provide other selective phases, including a number of aromatic phases, including phenyl, naphthyl, diphenyl, biphenyl, phenylhexyl, pentafluorophenyl, fluorooctyl, several helic phases. This enables the chromatographer to deal with co-eluding peaks by changing the column selectivity. And we've shown an example here of a sample run on a C18 where there are only appears to be 3 peaks in the sample, or 3 components, where there's actually a co-elution of 2 and 3. But if we change the stationary phase and go to a pentafluorophenyl or PFP, we're able to get resolution of all 4 components. We can also have changes in selectivity, and one of the common causes of that is a column temperature change, either through a faulty column oven or an unstable room temperature if a column oven is not being used. In order to stabilize that, if the separation is sensitive, that sensitive to temperature variation, it is recommended that a column oven be used. You can also experience changes in mobile phase, solvent ionic strength, additive concentrations, and pH variations. Another area that can cause changes in selectivity is injecting an excessive amount of sample or using a very strong solvent as a diluent for the sample. And a strong example of a strong solvent would be something like DMSO. Finally, the column itself has maybe deteriorated to the point where you need to replace the column so that you can get the separation back to what you expect. Another peak issue we see are ghost peaks. You can see the two chromatograms on the right portion of the slide. One is a newly injected sample, and we can see the peaks are sharp, even though there's a co-eluted peak or a partially co-elution peak at the end of the chromatogram. However, if we look at the next injected sample for this chromatogram, we could see an extra broad peak, and this peak is actually a carryover, and this carryover could be caused by a number of conditions, including contamination in injector or guard column. In this case, it is recommended that you flush the column with a stronger solvent to remove impurities, use high-quality HPLC grade solvents, and flush the injector, particularly when using an autosampler, between analysis. Another cause of ghost peaks would be lating eluting peaks from the sample of the previous injection. It is recommended to remedy this that you extend the actual runtime between analysis. If you're using isocratic mobile phase, that the column be periodically flushed with a stronger solvent. This is particularly true when using highly aqueous mobile phases, because organic material may build up on the column from the highly aqueous mobile phase conditions. It is recommended that under these conditions, that the column be flushed periodically with organic solvent to remove the buildup of any material, thus preventing ghost peaks from appearing. Another area would be under gradient conditions. And it is recommended that you end at a higher organic composition or a longer hold time to prevent ghost peaks from appearing in the chromatogram. Finally, ghost peaks can be caused by impurities in the mobile phase. It's recommended that you use HPLC grade solvents and to prepare fresh buffers. It's also very important that you check your water purification system or the quality of the water being used for your HPLC analysis. Finally, ensure glassware has no residual washing detergent. Next area that we'd like to discuss is retention time repeatability issues. Retention time shift, these are some of the common causes. We have the column, and that could be column degradation or contamination or just regular aging. It could be column overload. That could be due to actual injection volume or the actual concentration of the sample. Insufficient column equilibration. This is particularly prevalent during a gradient analysis when the column is not allowed to come back to equilibration after a very rapid gradient or a steep gradient. Finally, we have system and solvent. You have the mobile phase, can have change in composition, particularly from an older mobile phase. Let's say it's not prepared freshly, and it is recommended that mobile phases be refreshed periodically because they do degrade. Another area is that the pH of the mobile phase should be greater than 2 pH units away from the pKa of the analytes of interest. It could also have poor solvent quality, and again, not freshly prepared solvents. It could experience temperature fluctuations, a change in flow rate, and leaks. If you have a retention time shift, it's kind of important to pay attention. What are you actually saying? Is it flow rate dependent? If the retention time of an analyte peak and a T0 marker, such as uracil, which actually measures the void volume of the column, are changing to the same degree, it's likely it's related to some flow rate issue, such as a leak or some other failure of the system that's changing the actual flow rate through the system. If the T0 or the void volume measurer, and that could be, again, uracil, it could be the first column, first baseline perturbation, or an actual air peak. If you're using a UV detector, we can actually be sensitive to the refractive index changes. So if the T0 remains constant, but the analyte is changing, then it's probably due to some sort of chemical change either in the mobile phase or the column itself. If you have variable retention times, in other words, retention times that are random, increasing or decreasing and going forward or backwards, then you have some causes including insufficient column volume, fluctuating column temperature, poor system performance, and that includes, again, leaks, faulty check valves, or poor pump seals. As we can see here, there's a simple way of checking the flow on an HPLC, which we often recommend. It requires just basic equipment such as a stopwatch or some sort of timer and a graduated cylinder where you can actually measure the flow and see if it agrees with the flow rate that you have set for your particular analysis. Now, if you have a situation where you have an increasing retention time, we could look at some of the common causes, including changes in mobile phase composition, bubbles in the mobile phase itself, and that could be through poor peak pump seals or leaks in the system. You can have a decreased flow rate, again, for a number of reasons. Actual loss of the bonded phase, which would actually cause retention times to increase because we may be revealing active sites on the column through the loss of the stationary phase, and again, leaks. We could also have decreasing retention time. And that could be due to column overload. Again, a column issue such as loss of stationary phase. This would be particularly prevalent for neutral compounds where the retention of a neutral compound is completely dependent on the stationary phase. You can have an increase in temperature, which generally decreases retention time. We can have an increased flow rate for various reasons. And we can have a system issue, such as, again, faulty check valves and leaks and poor pump seals. And we could see some examples of a decreasing retention time shown in the chromatograms. The upper one shows increased tailing, and this could be due to a column degradation issue. And the lower chromatogram on the right side actually shows an overloading of the column. So it's important to adjust your sample size in order to obtain a stable retention time for your particular analysis. Another cause of retention loss is phase collapse, and this is exhibited particularly for highly aqueous mobile phase methods. We could see that we have a retention of amoxicillin shown on the left side chromatogram of around 8 minutes. But if we run the system and then allow the pump to shut down, we then experience a phase collapse, and when we restart the pump, we've lost the retention, or we decreased the retention for the amoxicillin. And this is due to the collapse of the stationary phase, which is incompatible with the highly aqueous mobile phase conditions. In order to prevent this, it is recommended that you utilize, if you are using a highly aqueous mobile phase or needed to use a highly aqueous mobile phase, it is recommended that you use an AQ type column, in this case an Aquacept, which is compatible with the highly aqueous mobile phase conditions and is resistant to phase collapse and will enable reproducible retention times run after run. Now I'd like to discuss baseline effects. You can have a noisy or unstable baseline. Some causes would include insufficient degassing or bubbles in the system, incompatible mobile phase with the column storage solvent. It is recommended that you go through your supplier's literature for your column and see what they recommend as a storage solvent. Make sure that the storage solvent and your mobile phase are compatible. For example, if the column is stored in acetonitrile and you require analysis in hexane, in other words, a mobile phase of hexane composition, these two are incompatible and you will experience a lot of noise and baseline upset. So it's important to go through an intermediate solvent such as isopropanol or THF before beginning an analysis with a hexane mobile phase in that particular situation. Another cause of baseline noise would be poor mixing or proportioning. Again, that would require system maintenance or some system engineer to look at your system and to make sure that you're able to obtain proper mixing. Mobile phase particulates, again, it's recommended that you use filters. Also contaminated system. Again, it's important to ensure that all parts of your HPL system are compatible with the solvents being used. And again, finally, poor system maintenance. Again, the excessive noise could be due to an old UV lamp or even a sampling rate that's too high for your particular analysis conditions. Another area that's a baseline issue would be baseline rise. The chromatogram shown here shows a typical baseline rise. However, it should be noted that baseline rise is normal for gradient analysis. But there are cases where the baseline rise is greater than expected, which includes insufficient equilibration when changing mobile phase composition, a strongly retained component in the sample, which can elute as a very broad peak and appear as a baseline rise. We can also get baseline rise from mobile phase contamination. Finally, we can have system contamination. That could be from tubing and other parts of the HPLC system. It is recommended that all components of the HPLC be compatible with the mobile phases being used for a particular HPLC analysis. If you have any questions regarding that, you should check with the manufacturer of the HPLC and explain which solvents are being used so that you can ensure that they are compatible. You can also have negative peaks or spikes. And if you're using a UV detector, these are sometimes seen. They could be from the surroundings. It could be from a faulty cable. It could be from an incorrect reference wavelength. You could also have vacant peaks. So you can have mobile phase that's more absorbent than the sample components. The sample solvent and mobile phase can differ greatly in composition. This would cause negative peaks or spikes. Again, if you have a storage solvent for your HPLC column that's not compatible with the mobile phase, you can experience noise spikes. An aging or faulty lamp, and also air bubbles in the system. And again, I would stress that the UV detector is not only sensitive to changes in UV absorbance, but it also experiences changes when exposed to different refractive indexes in the mobile phase or in the sample. That can cause a baseline perturbation of the chromatogram. Again, you could have negative dips, and we could see a negative dip in the chromatogram on the left side. This could be due to high background absorbance, due to using a low wavelength, which is not compatible with the sample or the mobile phase. Could be more experienced at high sensitivity, and again, could be a factor when recycled mobile phases are used. Another area that we need to look at when looking at causes and problems for HPLC systems would be column deterioration and how to prevent it or care for the actual HPLC column. Column deterioration can be seen through the loss of resolution, split peaks, poor peak shape, or high back pressure. Again, for loss of resolution and split peaks and poor peak shape, this is generally recommended that the column be replaced, or at least the frit be replaced for the column, or the column be cleaned to remove extraneous material. This is particularly true in the high back pressure situation. One of the ways to protect the column is to use guard cartridges. It is important, however, that these cartridges be changed at the first sign of back pressure or performance changes. Another good practice is the use of inline filters. Again, most HPLC systems contain some sort of inline filters, and it is important as part of the PM program that these filters be replaced, usually between 6 months and every year, or replaced when the pressure increases. Finally, it's recommended that the solvent reservoirs and the sample itself be filtered, particularly if it contains particulate material. We can see the example here of 2 chromatograms. The upper one is a retention using a guard column. It's a bit longer retention because we've added some stationary phase or some length of column as our guard column to particular analysis. We can see in the lower chromatogram there is no guard column being used. We could see a shorter retention time. This is perfectly understandable when guard columns are being used, and you should expect a slight change in your retention time, particularly when compared to the non-guard column situation. Finally, if you have a column that's deteriorated, it is worthwhile trying to clean or restore the column. We've outlined several steps here for cleaning and restoring of an HPLC column. First step is, and most important, is ensure that all buffers are removed from the column. And this is generally recommended as shown in the right portion of the slide in step 1, that the column be rinsed with 95% water, 5% acetonitrile to remove any buffers that have been used for the analysis. You can then proceed to step 2. If possible, unless the column is deteriorated, you should be able to run a QC test according to the column manufacturer's QC test that was enclosed with the column. If you're not able to run the test, I would still proceed and actually reverse the column to back flush it. And again, I would pick up at step 2. So of the right-hand portion of the slide where we begin with methanol. and again, proceed with the washing protocol according to the column manufacturer's recommended procedure. This is one procedure that we recommend for many of the C18 reverse phase columns, including washing with methanol, acetonitrile, IPA, acetonitrile, and then finally restoring the column with 80% methanol and 20% water. At this point, you should be able to run the actual QC test that was supplied with the column. At that point, you should decide if this test is acceptable or not. If not, then the column has to be replaced. If you're satisfied with the QC test, then you can continue with your analysis and ensure that all the mobile phases that are now used with the washing solvents are compatible, preventing any type of precipitation. So we think we can provide now a complete solution with the new PerkinElmer LC300 plus the EPIC columns, provide the ideal situation. We are able to offer the LC300 in two different pumping pressures, one at 10,000 up to 10,000 psi, which can be used with the 3-micron columns and larger. We are also able to provide an 18,000 psi maximum pressure system, which is ideally suited for the sub-2-micron EPIC columns. Both systems contain an auto sampler with high-performance features, including sample dilution features. Detectors are supported for both LC configurations, for both pump configurations, including a standard flow cell for majority of applications and an optional lower volume flow cell for the sub-2-micron columns. And finally, we feel that we can provide a variety of stationary phases, a variety of particle sizes for analytical analysis, including 1.8, 3-micron, and 5-micron. And again, as all of our products, these columns are scalable from the analytical dimensions all the way through preparative dimensions. So in summary, we've covered some of the common issues that we've seen with HPLC analysis, including peak shape issues, retention time variability, baseline effects, and finally column deterioration. To reach the root of the problem, do the obvious or the easy things first, and only change one thing at a time. Very important, you should perform or have performed routine PM maintenance every 6 to 12 months, depending on the usage of the HPLC system. Finally, follow column care instructions provided by the column manufacturer to maintain optimum performance. And with that, both Catherine and I would like to thank you for your attention.
Well, thank you, Catherine and Matthew, for such an informative presentation. Before we get started on the question and answer session, I'd like to remind our audience how to submit questions. You can submit questions by typing them in the Q&A box, which can be found on the right-hand side of the presentation window. Our first question is, how do you test the integrity of the column, for example, voids?
One of the best ways of testing the integrity of the column is to refer to the original column test chromatogram that was enclosed with the newly purchased column. So it really pays to keep track of those tests and to actually perform them according to the manufacturer's condition. Then you can compare your current column condition to when it was originally shipped to you and put into service.
Our next question is, what type of compounds are prone to peak tailing?
Generally, amine or basic compounds, basic organic compounds are prone to peak tailing, but in some situations, acidic compounds can also tail. And one point I would care to remind chromatographers or practitioners of HPLC is that the mobile phase should be at least 2 pH units from the pKa of the target analyte. In some cases, that will can reduce tailing, but then again, it does depend on the compound, and again, amines are very prone to peak tailing.
The next question is, what is considered high back pressure?
The first premise is you can have high back pressure or be considered to be high back pressure if you're generally about 20% away from the original operating condition of the column. And again, I would refer to the manufacturer's column test that was enclosed with the column. But generally, if you're more than 20%, then you're getting into a high back pressure situation. In some cases, I've seen that where the back pressure does go up quite rapidly and actually causes the pump to shut down. And obviously, in that situation, that is would be considered to be very high back pressure.
Our next question is, what is the typical pH limit or range of LC columns?
Yep, typically there are columns, and our EPIC columns are good from pH 1 to 10, but generally a lot of the columns that are on the market are usable from pH 2 to 8, particularly the older products, the legacy type columns. But a number of the newer columns do exceed that pH 8 limit, and in our case with our EPIC line, we do go up to pH 10.
The next question is, can we find out from the instrument if the detector lamp is nearing its end of life, and how long do they tend to last?
Lamps typically last about 1,000 hours of use, and yes, and depending on your manufacturer's instrument, you can tell if you're nearing the end of the life. One way is to look at the reference signal versus the sample signal with an air cell. In other words, no sample or no mobile phase in the cell, and if that reference to sample measurement ratio is greater than the recommended manufacturing condition, then your lamp's okay. But if that begins to narrow and becomes, let's say, less than 2 to 1, then your lamp is probably nearing the end of its life.
The next question is, if peaks tail too much, what are the disadvantages?
Oh, that's a good question. One of the disadvantages is it's really hard to integrate a tailing peak. So in terms of quantitation, it's really hard to get reproducible quantitation and measurable quantitation from a tailing peak. In addition, when a peak tails, again, it depends on the nature of the compound, but if it's let's say a basic or an amine containing compound, maybe that you need to try a different column to reduce that tailing. However, if you have a neutral compound that's tailing, that's kind of a serious condition, and either the column has a void in it, or your connections to the column are not proper, or your actual HPLC system needs maintenance, let's say pump seals or check valves of that such. So again, it really depends on what analytes are tailing. So if you see a neutral component tailing, that's quite a serious condition, and there's probably a fault in the system.
Our next question is, how do you select the mobile phase for drugs in salt form, and how do you generally select the mobile phase?
Yeah, that's really a good question in terms of your starting point for developing a new analysis. And again, I'll reiterate that the pH of the mobile phase, particularly if the pharmaceutical is of interest or the target analyte is ionic, it would have a pKa, and your mobile phase should be at least 2 pH units away from the pKa of the target analyte. In addition, generally speaking, the mobile generally let's say C18 columns are usually a good starting point for developing an analysis. And we generally recommend mixtures of acetonitrile and water as a beginning point. And again, you have to refer to your target analyte to see if it's ionic and such that you would need to use a buffer. Again, if you're doing a neutral compound, such as polyaromatic hydrocarbons, then you don't really need to use a buffer. And bear in mind, C18, the more acetonitrile you add, generally the less retention you have, particularly for a neutral compound. So you really have to adjust the levels of your organic to match the desired retention and separation that you require for your analysis.
Our next question is, while doing carbohydrate and sugar analysis using an RI detector, most of the peaks are not separating properly. Please tell us the extraction method and the good column to use to separate all the peaks.
Yeah, that could be very challenging. It depends on how structurally similar the carbohydrates are to each other, and if they're sugar alcohols or such. They could be very challenging separation. So generally, a starting point would be a column that's been specifically validated for carbohydrates would be one approach. Another approach would be using an amine column with a higher level of acetonitrile that may provide you with the separation that you require. In addition, you should look at the particle size of the column that you're using. Let's say if you're using a 10-micron column, that's a fairly older technology and is not going to give you really high resolution characteristics for many separations. So I would look at either going to a 5-micron column or a 3-micron column. In addition, some RI detectors have a large void volume associated with their detection cells. So I would look at the age of your RI detector, and if you really do need high resolution results or better separations, you may have to upgrade your RI detector to something that has a lower void volume, or dead volume, I should say.
All right, and the next question is, at the beginning, peaks are good, but after many analysis, they show some problems. Is the flow rate too low, for example, as a possible reason? Or because they were firstly good, you have to consider other parameters like, example, contamination, impurities, and so on.
Yeah, I would actually consider other contaminants, impurities, and so on, or maybe just the column degradation by itself. Flow rate generally, if you've established stable conditions and are pleased with the flow rate and the peak shape for the separation at the initial condition, flow rate is generally not a reason why your peaks have degraded. Now, of course, there may be faults in the system, and so you have to monitor retention time also. So let's say if a pump seal is leaking or something has developed a leak, yes, that is flow rate related, and you can actually have a lower flow rate as a result of that leakage from a pump seal or other parts of the system. So again, as we did in the presentation, if there's any doubt involving the actual flow rate that's going through the column, it's best to use a graduated cylinder and a stopwatch or a timer of some type and actually measure the volumetric flow and see if it agrees with the actual setting of the instrument.
The next question is, when running validated methods where the column type or the running conditions cannot be altered, what would be the most useful diagnostic steps for poor peak shape?
I think, again, I would refer back to the original manufacturer's column test, and I would actually go back and perform that test. That'll tell you if the column is working properly or if your system's working properly. So, you really have to look at both conditions. But I do understand that, there are restrictions with validated methods. In addition, unfortunately, there are variations in lot to lot for many manufacturers' columns. We try best to minimize those variations in our column production and the products that we sell, but there are exhibited variations, particularly when older products are used for validated methods. So it's important, again, to refer to the manufacturer's test chromatogram to make sure that your system and your column is operating properly. And again, if everything's fine, then again you may have to look at another lot, select another lot of the column and see if that reestablishes your peak shape, original peak shape conditions of your validated method.
Our next question is, why is ammonium phosphate, sodium, etc. buffers used in mobile phase?
Again, it's related to the pKa of the targeted analyte. And again, why specifically phosphate, ammonium phosphate, sodium phosphate? Again, sodium phosphate and sodium phosphate and potassium phosphate are used as buffers generally when UV detectors are utilized, and depending on what the wavelength is used for detection, these have very low UV signatures, the sodium and potassium salts of phosphate. The ammonium phosphate has a little bit of a higher UV signature, but is also useful in many cases. And again, it's used to adjust the pH, and again, trying to get at least 2 pH units from the pKa of a target analyte.
Well, unfortunately, we're out of time. I want to thank the audience for attending and for participating in today's event. I'd also like to thank our sponsor, PerkinElmer, for making today's educational webcast possible. We'd like to ask everyone in the audience to participate in a brief survey from our sponsor, which you can find on the right-hand side of your screen. You will receive an email alerting you when this webcast will be available for replay. We invite you to forward that announcement to your colleagues who may have missed today's live event. Thanks to all for joining. We'll see you next time. Goodbye.